now that we're through talking about Bailey, we won't say any more about him. Okay. All right. We'll start from the current slide. But before we go there, now this is for Bailey, but it's also for you, Lauren. I hope you're listening. One of the things that we had meetings Monday, Tuesday, and Wednesday. Well, Monday and Tuesday had office hours on Wednesday. And one of the things they were stressing like crazy, just to give you a little background, we have our SACS reaccreditation visit coming up in the next few years. It's not going to be immediate. Y'all probably, you'll be gone for sure by then. But one of the things they look at is, I really pay close attention to, is student course evaluations. And we've gotten a little slack in them, you know, just say, hey, please do them. Now they're wanting us to get up to close to 80%. And we haven't been that high for quite a while. So have you already done yours? Not yet. Okay, please do them. And so please. I did it during the summer term. You did? I did. Fantastic. Thank you. And please, all of you, all three of you, please do your student course evaluation. Because see, if one of you misses, well, I'm not 80%. I can't possibly get there. Okay, so I need all three of you to do it. Okay. But no, we really do value your input, because I feel like I get decent input, maybe not as much from Lauren as I do from the other two, because I see you every day, most days, and, you know, I find out if you have questions and that kind of stuff. But man, when the other offices on campus, like registration, that kind of stuff, library and things like this, they don't have much better input than what they get on that. So please do completely your student course evaluations. Fantastic. All right. The one other announcement I wanted to make was this one. Normally I have office hours on Fridays on the Birmingham campus, 7:45 to 11:45. Not this Friday. I have an infusion coming up this Friday, so I will be at Kirkland Clinic all day long. There's no way I'll be able to be at the Birmingham campus on Friday. Okay, so don't look for me there. All right. Any questions before we get started on today? Okay. What's that? What section are we in? We're in 8.1, Chapter 8, which is further applications of integral and Taylor polynomials. We're not going to do Taylor polynomials. We won't have time. But now we're doing arc length, and then we'll move to surface area today. Now, the one other thing I also want to say is what's coming up 1 week from tomorrow. No, I'm sorry, 2 weeks from tomorrow. Huh? No, that's 3 weeks from today. Our last class. No, that would be Wednesday. This Wednesday? No, 2 weeks from this coming Wednesday. I don't know. Oh, you better know. Okay. Yes, it's the special election for the U.S. Senate seat, and I want every one of you to get into the habit of voting every election we have. It is absolutely pathetic that usually on these odd elections like this, sometimes we as low as 20 to 30% of the people vote, and that's not a democracy. Okay. So I want you to get used to voting every time those polls are open. I try to. I may have missed 1 or 2 local election runoffs or something like that somewhere in my past, but most of the time I'm going to be there every time. Please vote. Please vote. I won't tell you how to vote or for whom to vote, but please get into the habit of voting. And that gives you plenty of time. If you aren't registered at your where you're currently living now, today is the last day you can register and still vote on the 12th. Okay, you can still register and vote in the next election, whenever that's going to be, but you can. You'll need to register today. You can go to alabamavotes.gov, G-O-V, alabamavotes.gov. You can also find out there your polling station and that kind of stuff. So please vote. And Lauren, if you need absentee ballot, you've got maybe one more week to get that. So please request your absentee ballot. I think that may be also at alabamavotes.gov, but you can find that online where that is. Please vote. Okay. All right, that being said, let's go on to example 2, top of page 445. And this is, this is your hyperbolic cosine function, okay? And I don't usually mess with these. However, if you did use the where we get hyperbolic cosine and sine, you know, here's the place you find that. The hyperbolic cosine, let me get my, oh, I can't write on this, I forgot. You know, we don't have a lot of time. I'm going to skip this one, okay, if it's okay with you. Okay. Let's move on to example 3. You can read example 2. It's pretty straightforward. It's fairly easy to do, but I'd have to go in and explain all of that to you, and it's just so much easier to use the exponential. But since they don't do it that way, I won't. Well, do you want me to do it that way? It's up to you. Okay, so let's go on and go to the next slide. This is example 3. So many times, Bailey comes in. Oh, yes, here he is. Okay. And this is after laying out last week, huh? Or the week before. Okay. Did you have a cold or something?
We had, I think we had that blood bowl last week.
Yeah.
And I was just, we got done and I was sick. Like I just we had to swim that day, so.
Goodness gracious. And did you wind up having to give blood?
We have to next week.
Next week. Looking forward to that, aren't we?
No.
Yes.
I was thinking of anyway. I was like, I need to get a tattoo or something.
No, don't. No, not that, you know.
Get the flu next week. So
Don't do that either. Fly overseas this weekend and come back. Yeah, that would be far better than the other 2 options there. All right. Yeah, I was afraid when you had said you were doing all that with the Navy SEALs and stuff. I wondered if he's going to get sick out of that, and you weren't here. But glad you're back. All right, we're on page 445, chapter 8, further applications of the integral, and 8.1 is arc length, and we're going to get the surface area, and I just hit the wrong slide. I mean the wrong button. Here's what I meant to hit. Okay. And we just decided to skip example 2 because it's hyperbolics. It's far easier to do with exponents, but, well, to me it's easier to do with exponents, but since they didn't do it that way, I would just go skip it. Okay. Now, here's what I was going to say about this one. A lot of times, okay, you cannot get an exact solution, okay? Remember what you had to have. You had to have a function that when you took its derivatives and squared it and added 1 to that, that needed to be a perfect square, okay? And that's a hard thing to get, okay? Here's a function, y is equal to sine x. It says approximate the length s of y is equal to sine x over 0 to pi, so you see that there, using Simpson's rule s sub 6. So we're going to do Simpson's rule, so let's remind ourselves, let me get my pen activated, okay, s sub 6. Someone remind me what that will be. Simpson's rule. 6. 1/3 starts it. Okay, delta x. Bracket. y0. Yeah.
Yeah. I have 4y1.
Right.
Plus 2y2.
Right.
Oops. Yeah.
Plus 2y6.
Plus what?
2y6.
Y6. That last one and the first one, you don't have a coefficient. The others you do. Okay. Now, they have shown the graph here, and which is pretty good, so let's go on and use it since they've shown it. They've already divided the interval from 0 to pi, that's where we're going from, 0 to pi. And what interval? How do you get that interval? The delta x. Remember that? B minus a, and b in this case is? That would be the a. Pi minus 0 over 6, exactly, and that would be pi 6. So they've done that for us. 1 pi 6, 2 pi 6, which is pi thirds, 3 pi 6, which is pi halves, 4 pi 6, which is 2/3 pi, 5 pi 6, and 6 pi 6, which is pi. Okay? So there's our interval. Okay? There's our delta x also. So what we have to do is evaluate the sign at this point, that point, that point, this point, this point, and this point. And fortunately, we know all those, don't we? Because we remember our trig, don't we? So that's 1/3 times, what's your delta x? Okay. That's what we just did. That's your delta x, pi 6. Okay? Now, yeah, we know what y0 is. What's it? 0. Okay, got that one. Plus 4 times, and what's y1? The sine of pi 6. What is pi 6? Sine of pi 6. Oh, you do.
Oh, it's a
Multiple choice for me, huh? Okay.
Is it √3/2?
No, that
Is
is,
it 1/2?
it's 1/2. Okay? Okay. It would have worked in this case, but it's not. But, okay. Plus 2 times what's your y2 here? Okay, this is y0, y1, y2, y3, y4. Whoa, these should be up here. That should be, yeah, yeah, okay.
That would be square root 3/2.
Square root of 3/2 plus 4 times, what's y3? 1, that's 1, plus 2 times √3/2 again. I mean, you can sort of look at that and tell those are the same values. That's why I said you almost could have gotten away with it, but you couldn't have. Okay, next. 4 times 1/2 plus 0. Okay, big number. Okay. Okay. So let's see if we can add these things together. This is going to be pi 18ths. Okay, is what that becomes. Times, well, 4 times 1/2 is 2. 4 times 1 is 4. And by the way, 2 times this, so that would be just √3. 2 times that will be another √3. Okay, the 4 times 1/2 will be 2. So it looks like we have 4 plus 4 is 8 plus 2 root 3. 8 plus 2 root 3. Saw that? Okay. All right. Nothing too pretty there, except you could factor out a 2. That would be a 9 here, and this would be 4 plus root 3. And that's about the only way I can think of simplifying that. So pull out your handy-dandy calculator and do 4 plus root 3. No handy-dandy calculator today, huh?
I had to change doors because my doors were shut. So
Oh.
I had to forget it.
Oh, okay.
So what we added?
4 plus root 3 multiplied by pi and divide by 9.
Divide by 9?
Yeah.
2.00086.
Okay. I think you may have needed a parentheses in there somewhere. Let's start again. If you are going to do it directly like I said, I thought you were going to put an equal after each one of those. But if you're doing it like this, open parentheses, 4 plus root 3. Close parentheses, multiplied by pi, and divide by 9. Anytime you have something like that, you have to put in parentheses. What I usually do is equal. Second?
So you said multiply times 5. And then that gives me 18.007. And then you divide it by 2.
No, 9.
9. That's right. Wait, yeah, it's still 2.
Huh?
I still got 2. Unless you want to do it.
Okay. Let me just take a look at that. Oh, wait. Let's see.
Because 4 plus pi over 3, all that times pi.
Oh, my goodness gracious. I was just doing the sine function. Sorry about that. Yeah. You have to do something to it first, remember? Let's go back. What you did was right while I was giving you wrong numbers. So let's erase all that. Okay, sorry about this. What we're integrating is not the sine function. Remember what we had to do? Here our function was y is equal to sine x. But what did we have to do first? I started off going through all this and then forgot to do it. First thing you do for a arc length. What we did was what we did was just estimate the area under the sine curve. That was the area under the sine curve. That's not what it's asking for. The arc length of that sine curve. What's the first thing you do? Okay, yeah, but to get it there. In a calculus class, when I say, what's the first thing you ought to do? Think you're in Cal 1. Derivative. Y prime is equal to, and here's the one we always love, cosine x. You got it. All right. Ding, 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 ding. Red letter day. Okay. And then what do we do with that? Square it. Okay, so y prime squared is, real simple, cosine squared x. Okay, and then what do we do with that? To get to that formula you wanted to? Add 1 to it. So y1 plus y prime squared is equal to 1 plus cosine squared x. Ugh. And now what we've got to do is then take a y'all don't have the formula in front of you, do you? Take the square root of that. All right. Yes. Right there. Okay. That's the integral we're going to be taking. The integral from 0 to pi of the square root of 1 plus cosine squared x dx. Okay. A lot more complicated function than what we were doing. All right. So what we're got to do, not this function, but that's what we're evaluating at each of these points. So let's start with, and we again, our S6 is going to be just like we did before, 1/3 times, why is the pen not writing? There it is. We did our interval before. Delta x is equal to b minus a over 6, or n, okay, which in this case is 6. This is pi minus 0 over 6, which is pi 6. All right, just to get it all on the board here. Pi 6, that's our delta x. Okay? Now, what we've got to do is each of these things at that point, just like you did before. But now this is your y. These are your y's, this thing up here, not sine. Goodness gracious, how crazy. Okay, so let's start with at 0. What is cosine of 0? 1 squared is, and add 1 to it, you get. All right, high level math today. 1 plus 1 is 2. Let's say this together, class. Okay. All right, and then it's the square root of 2, right? So that's your first part, square root of 2, plus coefficient. Do I need to write that again? Yeah, 4 times, why is my pen not writing? There it is. Okay, now, what we have now is the cosine of pi 6, which is cosine of pi 6. We're doing that.
Root 3 over 2.
Root 3 over 2 squared would be 3/4. And 1 plus 3/4 is 4/4 plus 7/4. So we have the square root of 7/4, which would be the square root of 7 over the square root of 4, which would be 2. Right? Okay. Plus, next coefficient, 2. And now we do cosine of 5/3, which is 1/2 plus 1/2 squared is, yeah, we did that. Right. That would be 1/4 plus 1 is 5/4. And the square root of that is the square root of 5 over the square root of 4, which would be 2. Okay. Okay. Whoa! All right. And I'll go on and that 2, but leave a 2 up there. Okay. Plus, what's the next coefficient?
0.
Say again? Okay, it's going to be 0. It would be a 4 times, okay. Give me the coefficient. I just said it.
4.
4. Okay. Now let's start over. Cosine of pi halves is
0.
squared is
0.
plus 1 is square root of 1 is 1. Okay. I figured that. So that's just 4 times 1. Okay. Okay. Plus. All right. What's the next coefficient? 2 times. Okay. And we start with cosine of 2/3 pi. You want to know?
No, square root of 3 over 2.
Okay, it's the same as this one. Remember?
Oh, 1/2.
Yeah, it's 1/2. It's only it's a negative 1/2. Right? What we're going with. Square it, and that becomes a
Positive.
what? 1/4 plus 1 is 5/4, and the square root of 5/4 again is the square root of 5 over 2. Okay, and again the 2's go out. Plus, the next one is,
6.
okay, yeah, but first is the coefficient, 4 times,
Negative 1/2.
uh,
Oh, no.
I think we did a, yeah, 1/2 was the last one.
Yeah.
Right, so this is
Square root of 3.
Square-
Negative square root of 3.
negative square root of 3 over 2 squared is,
Positive 3 over 2.
no, you square that too.
Positive 3 over 4.
Over 4, okay. Add 1 to it,
7.
7 over 4, and take the square root of it,
Square root of 7 over
2.
2.
All right. All right. Plus, second,
Negative 1.
okay, negative 1 squared is
1.
1. Plus 1 is
2.
2, all right. Square that. Square root of 2. No coefficient. The coefficient of 1, by the way. Okay. So there we have that. Ooh, boy, what a joy. Okay. This will be pi over 18, just like we had before, times. We got a 2 root 2, right? Plus 4 root 7, right? Plus 2 root 5. Okay. Plus 4. Right? I think we got them all done. Huh? What? Okay, right. Now, I mean, good. I mean, ask the question. I'm skipping a bunch of stuff.
Yeah, let's see.
Okay.
Adding them.
Yeah. Here's a root 2, there's a root 2, that's 2 root 2s. There's a 2 root 7 plus another 2 root 7, that's 4 root 7. Plus a root 5 plus a root 5 is 2 root 5 plus 4. Right? Okay. Now, one thing you can note here is you got a 2 in every one of those, so you can make this pi ninths times root 2 plus 2 root 7 plus root 5 plus 2. All right. Now, go back and do what you did before, and this will be, I can't think of an easy way to do it. So, root 2 plus 2 root 7 plus root 5 plus 2. I usually hit an equal sign at that point. If you don't, put them in parentheses before you add. Multiply by pi, divide by 9. Oh, I got to. Oh, the phone. Okay. Get an answer? What are we doing, huh?
first get the top one or
It didn't matter. This is a little bit simpler, but you don't have to do that. I just simplified it as far as I could. You could do the other.
I did the other one, and I got 3.819.
Yeah, they rounded 3.82. So that's approximately equal to 3.82. Now, I just have a sneaking suspicion, probably that's, well, Simpson's rule converges pretty quickly, so that might be what you need. A computer algebra system yields a more accurate approximation, 3.820198. So, yeah, that's good to 3 digits. So that's good. All right, makes sense? Sorry, I botched that. I talked about doing, but we just did the area under the sine curve, not the arc length of the sine curve. All right. Now, next thing we're going to do, hopefully, okay, correctly maybe this time, is find a surface area. Okay? Here's what we have. We have a function, y is equal to f of x, something like that. Whatever function that is, y is equal to f of x. And we're evaluating from a to b, so we're not going to do this part or anything beyond that, just this part. And what we're going to do is take that curve there from a to b and revolve it around the x-axis and try to get a surface area that you get from that. And as you might recall from doing things with axes of revolutions, you would do the length of that curve, which is now going to be an arc length around that. So basically, we do the same thing as before. We do a delta x dx, okay? And this is our y value. That's going to be the radius that you revolve around. But that's going to be your arc length, okay? Every little increment of an arc length, and then 2 pi times that y value. 2 pi times y is going to be the circumference for that y value. Well, that's not the 2 pi times the y value will be, that's the radius, but your function, the arc length there you do for the arc length formula, okay? So you have to do your incremental arc lengths times all that. So that's sort of the generic. We're actually going to do the one that we're going to do is this one. A lot more involved than the previous one, okay? And let's just get what we're talking about here. Okay, something about like that, okay? So we're doing a Grecian urn, no, laid on its side, and we're going to try to find the surface area of that Grecian urn. So we're going to be rotating the polygonal approximation to produces an approximation by truncated cones. Say this one here, they would pick the one that probably fits the best of any, but any of these you would do the same thing to, and you do that revolved around there, okay? Well, that would be your arc length revolved around 2 pi r, which is the radius, and just be your alpha of x y, whatever that is. They use this end. No, they use x y minus 1. They use that end. Okay? They did. Well, whichever they use. They showed that here and this one here. And that's what you're revolving around. There's your delta x of pi down there. So rotating that polygonal approximation produces an approximation by truncated cones. Not going to be exact. It's going to be an underestimate of your surface area, because the surface area is always a little bit longer. The arc length is longer than the straight line. We do that. Okay. So that's the procedure. What is the formula that you get from that? Okay. All right. So first they're going to do this truncated cone. Okay? That is what they call a truncated cone there. It's not exactly the same as the urn was, because the urn has a little curvature there, but it's going to be close. So there's a truncated cone. That's what we're going to approximate. Okay? Whoa, they skip right to the meat. Okay? And why they go through all that, I have not figured out. So I'd say let's do exactly like they did. Skip to it. You know, all that other stuff they do is perfectly correct, but what we just described is what your final answer is going to be. Okay? That surface area, and I swear I don't know why they take you through all the agony of a truncated cone. It's not hard, but it's just extra steps. But what we just said before, 2 pi r, where your r is that function value, times your incremental arc length. And your incremental arc length is 1 plus f prime squared, the square root of that. No, why mess with a truncated cone? You don't need it. It's just the 2 pi f, your y value there, and you're going from A to B, and your incremental arc length is the square root of 1 plus f prime squared. Just exactly what you had before, right? Only 2 pi r in front of it, and that gives you your surface area. So why in the world did they go through all that agony of that that whole page there on drawing the cone, drawing the surface area of it, and then doing the ratios and all like that? You get right down to the same thing we had before. So why go through all that? This makes sense a lot more than the other to me. All right. Now here we're going to do, take this arc, which happens to be a semicircle. Okay? Calculate the surface area of a sphere of radius r. Okay? Well, what we're going to do is put that sphere, center it on the origin, 0, 0, and radius r would be, it cuts through the xy plane at this right here. This is r here, r there, and this height here is r. So that's the radius, all right around it. Now, your f value anywhere here is, this is half of a circle, and the function of a circle, the circumference of a circle is, let's not go that route. The f of x, the value, any value x here, we know this has got to be r here, 0 here, and 0 here. That's your x. So what is that? Let's draw us a little triangle here. Oh, I can't draw it here. Let me draw a little triangle here. Okay. Now this is the point we're interested in, f of x, at any value x down here, from 0 to r, right? And what is this value going to be, the height going to be there, the vertical line there? What is that going to be? Well, this we know is r here, and this we know is x down here, right? So what would this, and this is a right angle here, right? Two perpendiculars crossing. Okay? So what would be your f of x here, this height here, this height here? Square root of r squared minus x squared. That's exactly what we've got to do. Right? So there's your f of x. Okay? Square root of r squared minus x squared. Now what did they say to do with this? Calculate the surface area of a sphere of radius r. Well, this is the curve that you're going to rotate around the x-axis, right? Now, and that's going to give you your sphere. Are you okay with this? That whatever the surface area is on this side, on the negative side, is going to be the same as the surface area on the positive side, right? So rather than going from minus r to r, let's just go from 0 to r and double it. Okay? So we're going to take the surface area of that function there, and this will be, the surface area is going to be 2 times the surface area here, and what would that be? You have to remind me. Last formula we came up with. Second? The surface area of this part right here. I can't draw very well, but you got the idea. That surface area there. When you rotate that. What was our formula at the bottom of the previous page? Hint, hint. The area of a surface of revolution formula. 2 pi. And what would that be in our case? 0 to r, exactly. Now, we're only going 0 to r because we're taking twice from r to r. Okay. Okay. And then what goes in here? Your f of x, which in this case is the square root of r squared minus x squared. Okay. And what goes here? The square root of 1 plus. All right, we got to do that, don't we? So f prime of x, and I think I'm going to rewrite this to be r squared minus x squared to the 1/2. Is that okay? You okay with that? Now take the derivative of that, and what do we get? One half times r squared minus x squared negative 1/2. That it? Net times second. Okay, now the r is a constant. So don't take a derivative of a constant. That's 0.
So r squared minus 2x?
Minus 2x, exactly. Okay. No, not r squared. That's a constant. Derivative of the inside is just minus 2x. Okay. Well, the 2 and the minus and the 2 there go out. So that leaves us with, this thing is, I'm going to go back and write it probably poorly, x over the square root of r squared minus x squared. You don't have to go back to this, but that's what that turns out being, right? So we took the derivative of it. What's the next thing we do? Not yet. Square it, okay? And when you square that, what do you get? So f prime of x squared is what? 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 Okay, a negative times negative is positive, okay? And then x squared over r squared minus x squared. That's it, exactly. And now what do we do with that? Add 1 to it. Plus 1, okay? Okay? Now, what will that give you? It's kind of a big boo hiss, but here's what it gives you. Well, it's not too bad after all. That would be a x squared over r squared minus x squared plus, what's another way to write that 1 as a fraction whose denominator is r squared minus x squared? R squared minus x squared over r squared minus x squared. Isn't that true? That's 1, right? Strange form, but it is true. So now that we got common denominators, we can keep the denominator, r squared minus x squared, and add the numerators. Well, here's a x squared and a minus x squared, so that just leaves you r squared, doesn't it? That's looking pretty good. So, without doing all that, okay, let's just cut to the chase here. And what goes there next is exactly this, right? We did everything we were supposed to. This would be times r squared over r squared minus x squared. And that would be times your dx, right? Okay. Now, this will be, I'm going to go on and multiply those together. 4 pi, you buy that, right? 2 times 2 pi. Okay. The integral, 0 to r. Now, just an observation. That denominator is the square of that part right up there. So that would then be the same as the integral of, and by the way, the r squared, let's go on and pull that out here too. You okay with that? That's just a constant. It can go outside the integral. No, just the r squared. That numerator there. Right? Just that numerator. The constant. Okay? That can come out, right? And what you have left here is r squared minus x squared to the minus 1/2 dx. Isn't it? Oh, okay. If you pull out the r squared here, because that's just a constant, just a number. Okay. Okay, that goes on outside. There's no x in there, so it's not going to be involved with that. Okay? And you have a square root of this over that. Well, that would be, if this is that thing, the square root of this thing squared, which is what it is, and then you wind up with just this in the denominator, which I'm writing like that, right? Okay, now we need to integrate that, an antiderivative of this. And what would that be? Oh, wait. Getting a little carried away here. You can't integrate that directly, can you? I think it's probably better. Sorry about that. I was trying to be slick, but slick was not good here. Okay? This goes back to being 1 over the square root of r squared minus x squared, which is exactly what I had before, but that doesn't integrate directly, does it? What would we need to do to integrate that directly? Yeah, that one. Say again? Trig substitution, perfect. Yeah, so I'll leave it alone. Okay. That'll be, and what would be your trig? Let's do this over here. Okay. Okay. What would be your trig substitution? They look back and forth. Say again? No. Yeah. If it had been x squared minus r squared, secant would be your ticket. It's a sign. Let x equal, except it's r sine theta. And just to follow through and make sure this is the right one, that would imply that since you don't have x, you have x squared. X squared would be what? R squared times sine squared theta, right? And then if you did r squared minus that x squared, so r squared minus x squared would then be, my nose is itching, must be going to have company. That would be r squared minus r squared sine squared theta, right? And then what could you do with that? Second? Yeah, factor out r squared. Okay. Now you want to go and put it under a radical? We could if you wanted to. We could. It sounded like that's what you were talking about. And then you would be pulling out an r. And what would be left under the radical? Got it? Minus. Okay, what's 1 minus sine squared theta? Cosine squared theta. And square root of cosine squared theta is? Cosine theta. So this would be r cosine theta. Very good. So that's your, well, no, one more thing. We need to do what dx is. If x is equal to r sine theta, what is dx? R cosine theta d theta, right? Is that right? Okay, what does that give us then? Our dx is r cosine theta d theta, and our 1 over square root of r squared minus x squared is 1 over r cosine theta. Oh my goodness. And what happens here? This gives you, oops, oh wait, I'm sorry. You got an integral here. Now, I didn't change my limits. Let's not yet. What would that give you? Theta. Okay, so this is going to be theta, a value, okay, theta. Let's just leave the theta for now. Well, what is theta? To this, yes, we have x over r is equal to sine theta, so theta would be the arc sine or inverse sine of x over r. Okay, so that would be inverse sine of x over r, and we're going to evaluate that from 0 to r. Okay, so we have our 4 pi r squared out front from long time passing. Okay, now let's evaluate that. When x is equal to r, what does this give? X equal r, what does that give? 1. And inverse sine of 1 is? Say again? 1. I would think not. The sine of what is equal to 1? Not quite pi. Pi over 2, exactly. So that would be pi over 2, right? Pi over 2. And what's when Rx is equal to 0, that would be, inverse sine of 0 would be sine of what angle gives you 0? 0, okay. All right. So let's see what we've got here. This is equal to, 2 will go into that twice. Where do I get a pi squared from? Should be 2 pi r squared. I know, but our answer should be that. No, it should be 4 pi r squared, not 2 pi r, pi squared r squared. Oh my goodness. I did this, no? Wait a minute. Okay, I did something dumb here. I'm trying to figure out what it is. I know. I see what they do. And let me see how I messed that up. It was in our little mucking around here. It's what I started to do, and I thought I had it wrong. And maybe I was right all along. Your f of x is that r square root of r squared minus x squared. All right. Got it. Okay. And then this thing was r squared. I had it r squared over that. They have it r squared over. Oh, yuck, how stupid. What I forgot to do down here, we got 1 plus f prime squared. I forgot to take the square root. That's what goes in the integral. You're supposed to be watching out for me, watching out for my back. And what did you do? Let me just carry on like crazy. This is supposed to be a square root. Well, the square root of r squared is r over the square root of r squared minus x squared. So that then, we don't have to do the trig substitution. Why did you have me do that? Okay. You just wanted to review that. I know. Okay. So we don't need that. We don't need any of this, I don't think. Yeah, we didn't need that. That's what I thought. It should come out much simpler sooner, and that's why I started to go right to the integration, but I thought, wait, you can't do that from here. You can't get there from here. Okay. So, this is where, okay. I think this is so much easier than what we're making it out to be. Okay, sorry about that. Okay, this was supposed to be here. Excuse me. You awake yet? Okay. Okay. Palpitations. Sorry. All right. These go away. You don't have them anymore. Sorry about that. Okay. And all you have then is 4 pi times the integral from 0 to r of r dx. Well, pull out the r, folks. So that would be 4 pi r times the integral from 0 to r of dx. And what would that be? Sorry about that. Lots of erasing today, huh? Must be Thanksgiving. All those turkey enzymes, okay? What does this give you?
Yeah.
4 pi r. And what do you say? Integral of dx. X. Evaluated from 0 to r. And what does that give you? R. So you get 4 pi r squared, which is the surface area of a circle. 4 pi r squared.
Okay, how do you,
Huh?
and like, so you get surface area of something that's 2D.
Say that again.
So that's the surface area of a two-dimensional figure.
Okay. You're taking this and revolving it around the x-axis. Taking this arc here, the semicircle, which has the F value here is that. We did that earlier. Okay. Now that's what you're revolving around the x-axis. So what does that mean? It's 2 pi r. The r here is not that r. It's the radius here. It goes from 0 up to 1 and down to 0 again. It's your f of x. So 2 pi f of x. Okay, that's going to be the circumference of this thing times the arc length of that. So that's what we had. 2 pi times your f of x, which was simply your f of x was this thing right here. The square root of r squared minus x squared. Okay, times, that's where we did our incremental arc length. Okay, and what we had to do there was first take the derivative of the f of x, then add 1 to it, then square it, then add 1 to it, then take a square root, which is what I forgot to do, and that left you with this thing. So that whole mess there was getting that arc length, the incremental arc length there. And this is what it comes out being, r over the square root of r. So that's what we put in here, times dx. These go out, this is the integral of that, pull the r on the outside, and you just got r 4 pi r squared. Much easier than what was trying. Yeah, what a waste of time. Sorry about that. Okay. Second time I've done something dumb today. Okay with it? All right. Now, example 5, they don't have on the slide set. I don't even think they had it in the older edition. In the older edition. And we got the newer edition, so let's erase. Can I erase all this, or you got it? Okay. Sorry about that. Okay. Example 5. Find the surface area of a surface called a paraboloid. Oh, we remember those, don't we? No. No, that's going to be the beginning of Cal 3. Sorry. My other class already knows what that is. You don't. That is obtained by rotating the graph of f of x is equal to the square root of x, which will be not this picture, but it'll be this one. So what I think I'll do. Okay. Not this curve, but this curve. Okay. Okay. What in the world is wrong with this picture here? Okay. All right. Okay. Let me start over. All right. The pen. Okay. Not going. Goodness gracious. It says I have the pen. Okay. Not that. Okay. And really not this either. You kind of turn this around, and what we have is a parabola that goes like this. And this is not ours here either. Okay. That's your parabola, and that parabola is f of x is equal to the square root of x. I'm going to write it as x to the 1/2 power. Is that okay? And what we're going to do, that's just this arm up here, not the lower arm. It's just this arm here, square root of x. Half of a sweeping parabola. Okay? And what I'm going to do is rotate that about the x-axis. Okay? So we want to get the beginning of a paraboloid there between x equals 0 to x equals 1. Okay? So from there to there. Okay? And rotate that around the x-axis. Okay. Now that shape is called a paraboloid. You don't need to know that for the problem, but that is what the shape is called. Okay? So this f of x is not there. There's the f of x we use. What's the first thing we're going to have to do to it? Take a derivative. So f prime of x is going to be second? 1? 1/2 x to the negative 1/2. Okay, tag team champions here. Okay. All right. Now what do we do with that? Square it, is that what you said? So f prime of x, f prime squared of x is going to be okay, let me write this differently. 1/2 the square root of x in the denominator, right? Is that what we got? That's your f prime. And when you square that, what do you get? Yeah, 1 over 4x. It's down in the denominator. You say 1/4 x, it sounds like it's 1/4 of x up here. It's 1 over 4x. Okay. 1/4 1 over x. Okay, or something like that. And then what do we do with that? Add 1 to it. Okay, and that would give you, if you add that 1 as what? 4x over 4x, that would be 1 plus 4x over 4x. Agreed? And then what do you do with that? Square root of it. Okay, you root it out of there. Okay. Now, I'm going to change this ever so slightly. I'm going to factor out the 1/4, which will be a 1/2 here. And that will leave me under the radical 1 plus 4x over x. Right? Agreed with that? Okay? Now, what our integral is for the surface area is what? Two pi times the integral from 0 to 1 of, second, x to the 1/2, that goes up here, times, can I write it like this? 1 plus 4x to the 1/2 over x to the 1/2. Can I write it like that? Whoops, and I had a 1/2 in front. There we go. Okay? Is that all right so far? I just rewrote this here. I pulled the 1/2 out front. That wiped out the 2. I wrote this as square root of 1 plus 4x over square root of x. That square root of x, that square root of x, they don't cancel each other out, or divide each other out, or wipe each other out, or whatever. So those are gone, and then you have a dx here. Okay? Now, I think we can evaluate that integral almost directly, can't we? Let me write it again for you so it's a little easier to see. That's going to be a pi times the integral from 0 to 1 of 1 plus 4x to the 1/2 dx. Isn't that what we've got? How would you do that integration? Second?
Do we do trig substitution?
I think it's easier without it, don't you? See, with trig substitution, you really need an x squared in there, in that radical. We don't have an x squared, which I kind of like not having. What would you do here? Leave off the trig of what you answered before.
Substitution.
Yes, let's just do a substitution. What would you substitute? Let what?
That u equals 1 plus 4x.
I like it. Okay, then
U
du is equal to?
what? Yes.
No, 4 dx. The 1, you take a derivative of 1, you get 0. Okay? All right. But we don't have a 4 dx, we just have a dx, so what do we do with that? Divide by 4. All right. Now let's see what we got. We got equal to pi in front, the integral. Let's go on and make our substitution here. As x go, when x is 0, what's u? We're substituting x's to u, so let's go on and change the limits here. When x is 0, what's u? 1. So that'll be going from 1 to 5. Okay? And what would be your integrand then? U to the 1/2. Oh, we got that 4 out here, du, isn't it? So we had a dx is 1/4 du, so bring the 1/4 on the outside, leave it in there. I think we can do that integral, can't we? Be pi fourths, and what would that be? Second? Second? Okay. Yeah. Okay, so you have u to the 3/2, and then you have a 2/3 here, right? Okay. Well, what I'm going to do is take that 2/3 on the outside, if that's okay with you, and that will make that a pi 6. Pi 6, and then we'll evaluate the u to the 3/2 from 1 to 5. And the 5 part stinks, but the other part's not too bad. So this will be pi 6. Whatever 5 to the 3/2 power is, okay, minus 1, right? And that's exactly what they got. Pi 6 times 5 to the 3/2 power minus 1. They put it in parentheses, I put it in brackets, I don't know why. So if you got your calculator, you know how to do 5 to the 3/2 power on the calculator. Okay. How would you do it? Just tell me.
On my calculator, I would just put it in, but you can also either 5 to the 3rd and times the square root, or
calculator field need to say 5 carat 1.5. So the 3 has 1.5. So 5 raised to 1.5 power. So whatever that is, subtract 1 from it, multiply it out, pi and divide by 6. You get what? 5.3304, you said? That's exactly what they got in the book. You must be, never mind, okay. You're close. You don't have your charger?
I left it at home.
Oh, I see. All right, very good, excellent. Okay? Let's move on to example 6. And this one we do have a slide for. There it is. Good old bullet looking thing here. Find the surface area S of the surface obtained by rotating the graph of, oh, what a beautiful graph this is. Let me go on and blow it up so you'll get full appreciation for this function. S is one of my favorite functions of all time. X to the 1/2 minus 1/3 x to the 3/2. What a nice function. Okay? Now, because I'm somewhat of a cynic, I want to just see if this even is making, if their picture is even making sense. When x is equal to 1 here, square root of 1 is 1, minus this thing is still 1. And so that would be 1 minus 1/3. So this would be 2/3. It's 1/3, 2/3. That looks about right. Okay? And when x is equal to 3, you have the square root of 3 minus 1/3 of the square root of 3 cubed. Right? All right. Well, let's cube 3 first, and that gives us 9, right? I mean 27. Okay, sorry about that, 27. So 1/3 of 27 is, can you do that? Yeah. And the square root of, that's not quite right. I'm getting things out of order here. So what we have here, we got this one, that was 2/3. I'm going to have to shrink back. Okay, so when x equals 3, you have x, or 3, basically the square root of 3, minus 1/3, the square root of 3 cubed, right? Okay. No, you don't need to do that. It's real easy. Square root of 3 minus 1/3. Well, this is the square root of 3 squared times the square root of 3, right? Is that square root of 3 cubed? Square root of 3 squared times square root of 3. What's the square root of 3 squared? 3. And 1/3 of 3 is 1. So you have square root of 3 minus square root of 3, sure enough, is 0. Yes, so this looks like it might be the right thing. I didn't try the points in between, but I'm hoping it'll be a nice smooth curve like that connecting the dots. 1/3, okay. So I feel okay about it now. I was really beginning to doubt if they had it right, but I think they do. So let's say that's our thing here, and we want to find the surface area obtained by rotating that graph around the x-axis from 1 to 3. So I think we got it all right. What are we going to have to do? What are we going to have to do? Think of this as calculus 1. What's the first thing you need to do? Take a derivative. Very good. Y prime is equal to 1/2 x to the negative 1/2. Very good. Minus, which is 1/2. Okay, very good. The 3's cancel out. Okay. 1/2 x to the
5/2.
okay, you're taking a derivative.
5/4.
You're taking a derivative. You reduce that by 1, which is 1/2. Very good. With a little property. Okay. Now, just to make things a little bit better, and you might not think they are, I want to write it like this. First, let's pull out my 1/2. That's common to both of them, right? Now, the first one is going to be 1 over the square root of x minus the square root of x, right? You agree with that? Okay, so this is going to be 1/2 times. Well, what are we going to have to do if you're going to subtract fractional forms here? What's that? Rationalize? Oh. I'd rather not. I don't know if that would help you or not. Well, the need is least common denominator, isn't it? What's your only denominator? The square root of x, right? Okay. Now, if I want to put this over the square root of x, I have to multiply the numerator by square root of x too, right? So what would that give? X over square root of x. So this will be 1 over root x minus x over root x. Would you say that's okay? So that would be 1/2 1 minus x over x to the 1/2. I'm mixing up my notations here, but that's what you get from that thing, from the derivative. Okay? And then what do you do once you get that derivative? Square it? Is that what you said? Yeah, let's square it. So the y prime squared is going to be square root of 1/2. Square root of 1/2. Second? 1/4. Let's square the numerator. I'll just do it that way. Square the denominator. X. I like it. Don't you? Okay. So another way to write this is 1 minus x squared over 4x. You okay with that? Okay. Now what we got to do with that? Add 1 to it. So plus 1 plus 1. Okay, but let's write that 1 as what? How about 4x over 4x? I like that better too, okay? You could do it the other way. Well, no, I think it's better like this. So this is, let's go on and multiply that out. That'd be 1 minus, second, 2x it's a plus, x squared minus 4x, right, over 4x. You buy that? Okay, what would that be? 1, oh, that's a plus 4x, isn't it? Yeah, sorry about that. 1, okay, these two you can combine, plus 2x plus x squared over 4x. So that's what that is, right? You buy it? Okay. And what are we going to do with that then? Say again? Square root it. Okay. But what is that numerator, by the way? Does that look familiar? Isn't that 1 plus x squared? Because this very thing, except with the minus sign in there, that was your 1 minus x squared. So this becomes 1 plus x squared, right? Over 4, 1 over x. I'm writing it that way for a purpose, because we're going to take a square root of it. Isn't that what you said? And what's the square root of that front part? Square root of 2 perfect squares would be 1 plus x over 4 times 1 over the square root of x. I don't know if you want to write it that way or not, or you just want to write that as 1 plus x over 4x to the minus 1, x to the 1/2, or something like that, right? So that's your arc length increment, right? Okay. So let's go back to the top and do what your surface area is. And what is your surface area? 2 pi, I like that. Integral from 1 to 3 of what? The original function there. All right, so let's write that as x to the 1/2 minus 1/3 x to the 3/2. Okay. Times 1 plus x over 2, actually, that's a 2 there, not a 4, 2 root x dx. Do you buy that? All right. Now. What I think I'm going to do is pull that 1/2 that you have in that second part there out front. Why not? 2 is just messing things up. Pull it out front. That's going to wipe out this one. You okay with that? Okay. So this will be pi times the integral from 1 to 3. Okay. Now what I'm going to do, I'm going to leave the 1 plus x here, right? I just shifted it around some. And I'm going to do this like this. This one here is going to be, let's write it as x to the 1/2 minus 1/3 x to the 3/2. But I'm going to split this and do over x to the 1/2 here and over x to the 1/2 here. Is that okay to do? Basically, I'm doing this by that, so I'm going to do it over here minus over here, right? Is that okay? All right. Now, I think that I'm missing the dx, but other than that, I'm fine. Okay. All right. Okay. What is this? X to the 1/2 over x to the 1/2. 1. Okay. Minus, I think the 1/3 is going to still be there. But what's x to the 3/2 over x to the 1/2? Say that one more time. X. Stop there, right? X, right. Okay. What would you do here? It's just really a fairly simple binomial. Only a little screwy thing with it. That's a 1/3, not a 1/2. Where did the 1/2 come from? I'm not sure. That's a 1/3 there. Okay? Let's just multiply. FOIL that, those two binomials, right? It's going to be a little messy with the fractions, but we can live with that, can't we? So 1 times 1 is 1, okay? And the outers, 1 times a minus 1/3 x is a minus 1/3 x, right? And then the innards would be plus x, right? And then you got a minus 1/3 x squared. So this will be pi times the integral from 1 to 3. I think this is going to be 1 minus or plus 2/3 x minus 1/3 x squared dx. Can we integrate that? That's the question. I hope I won't need this again, because I sure don't want to try to think, what in the world, how did I get there from here? Okay? This is going to be pi. Antiderivative of 1 dx. X, very good. Antiderivative of 2/3 x. Two-thirds, I heard very quietly. X squared. Over 2. All right, finally got it all out. All right, and the 2's go out, right? They've been dating. Okay. Then the last part. Cubed over 3. Okay, got it? So this will be evaluated from 1 to 3. So this is going to be pi, let's see if I can clean this up just a little bit, be x minus x squared over 3 plus, minus, yuck. I got mine backwards, didn't I? I hope I didn't do something dumb there. Seems like my signs are off, but I guess it's right. No, I think that's right. Okay. Minus 1/9, or x cubed over 9. And evaluate from 1 to 3. It's going to be pi times what? 3 plus 3 minus 3, okay. Y'all are sort of stuck on 3's, aren't you? Then minus 1, and it's a minus, so remember subtracting, minus 1/3. But then this next one is plus 1/9. Okay. Now, I'll get rid of some of those 3's there. So that gives me 3 1/9 minus 1 1/3, right? So this would be 2 and 10/9 minus 1 3/9, right? Would be 1 7/9, which should be 16/9 pi. Oh my goodness, look at that. They got it right. Don't forget your pi that was hanging around in front. Got it? Okay. Well, kind of the bad news here, folks. We're out of time. Okay. Get over it. All right. There are 5 preliminary questions. You want to start with those next time, or you want to do those at home, and we'll start with 8.2? You tell me. Start with 8.2? All right, well then let me give you your homework exercises. Do either 1 or 3 or both. Any of the odds 5 through 9. Any of the odds 11 through 15. Any of the odds 17 through 33. Any of the odds 35 to 41. And it says you need a computer algebra system to do these, but you can work with them what you can, either 3 or 45. And then do either 47 or 49, or both. All right, and next time we'll start with fluid pressure and forces. Okay? Good deal. Any questions? Okay. Then we will get out of this one. Okay. And okay. Let me end our recording.